Welcome to our project. It is called Oracle of Artists. We're team Drop Top Hash Map. My name is Jay Rajpal, and I'm working with
Jessica? Lisa?
And below.
So our project was inspired by the Oracle of Bacon and Boiled Frog. Oracle of Bacon is a website that lets you input two different actors, and it provides the link between the actors based on movies that they've worked together on. So, for example, if you input Tom Holland and Alexa Demie, it would show that Tom Holland is linked to Zendaya through Spider-Man, and Zendaya is linked to Alexa Demie through Euphoria. So it would show how the actors are connected. And then Boil the Frog is another website that's connected to Spotify, and it allows you to put two artists, and it generates a random playlist that transitions from one artist to the next. So we basically took these ideas and put them together, and we wanted to be able to input two different artists and create a playlist that connects one artist to another based on songs that they've collaborated on. So that was kind of the basic idea. And we wanted to find connections between artists based on the collaborations and also just learn more about them and how they collaborate through different graph algorithms. So the data set that we used was from Kaggle, and it contains data on about 1.2 million songs from Spotify, and it was obtained using a Spotify API. And each row of the data set basically contains the song name, the artists that have worked on that song, as well as other features like danceability, energy, etc. So we basically just got rid of all the columns that we weren't going to use, and we only retained the song name column as well as the artist name column. And then we also got rid of the songs. We just cleaned up the data and we got rid of the songs that contained only one artist, because for the purpose of our project, we were going to, the way we set up our graph was essentially the nodes were going to be the artists and the edge was going to be the song they collaborated on. So if only one artist worked on the song, then you would just have an unconnected node with no edge. So we got rid of those. And then we just did some data cleaning because, for example, we were using commas as the delimiter when reading in our CSV. And for example, if there was a comma in the artist's name, then it would be separating that artist where we didn't want it to be separated. So just in order to make sure that our graph was being created properly, we had to do some cleaning. And we ended up with a CSV that contained about 95,000 rows.
So in this project, we implemented four different concepts. The first is we wanted to find the shortest path between two artists, and we used a breadth first search to implement this. The second thing we wanted to do was create a playlist between two artists. So we used Prim's algorithm for minimum spanning trees to do this. The third thing we wanted to do was calculate the Bacon number for an artist. So we used betweenness centrality for this. And the fourth thing we wanted to do is find the most popular or important artist. So we use PageRank for this.
So the first thing we had to do after cleaning the data was create a graph. And we wanted to create a basic graph which had nodes and edges, so vertices and edges, connecting different nodes. So we loaded in the clean to CSV and parsed through the data using comma as a delimiter, which meant if we had two different artists, we separated them using a comma and split it using the comma to understand one artist was artist one and the second artist was artist two on one singular song. So edges are songs. So the things connecting two nodes, which are artists, is a song. And this resulted in an unweighted, undirected, unconnected graph of artists, which essentially it has connected components, but it's not all connected to each other. And at first iteration, our graph only implemented two artists per song, but we recognized that songs have more than two artists, like 3 artists, 4 artists. So our second iteration of our graph could handle a vertex of artists. And we used GraphViz to render our graph.
So basically, the first thing that we wanted to create was a playlist where the user would input two artists, and then based on songs that they've collaborated on, it would create a playlist connecting one artist to the other one that was inputted. inputted. So in order to do this, we realized that we would need to find the shortest path on an unweighted, undirected, and unconnected graph. And in order to do this, we implemented a BFS algorithm. So we just did a traditional BFS implementation using a queue. However, the BFS, essentially, when it traverses through the graph, it visits each adjacent node of the node that it's on before moving on to the next node. So it doesn't necessarily trace the shortest path. So in order to fix that, we kept track of the paths that it was visiting we first had a map of vertices that kept track of which vertex was connected to which parent vertex. And then we also had a map of distances that kept track of the distance that each node had from the source node. And the source node was essentially the first artist that was inputted. So using that, we basically were able to print out the shortest path at the end of the algorithm.
So we wanted to explore another way to create a playlist when you input 2 artists, and we decided to use Prim's algorithm for minimum spanning trees. So essentially, we wanted to create a playlist of every node in a connected component with no cycles, which contains the minimum number of edges or songs required to hit every artist in a connected component. We begin by creating a priority queue with the starting vertex as the first element, so the first artist you input, with a weight of 1. And for each vertex in the priority queue, we check its neighbors and add them to the priority queue if they are not already in it. We assign each neighbor a weight of 1 since our graph is unweighted, and from the starting vertex to the neighbor. And we then remove the vertex at the front of the queue and look at its neighbors. For each neighbor, we check to see if there's a shorter path from that vertex to the initial vertex. So every vertex we check if the edge next to it has a shorter path. If there is, we update the edge weight of the neighbor in the priority queue and add the new edge. And then we repeat steps 2 and 3, so the last 2 steps, until the ending vertex is reached.
Another thing we wanted to do was calculate the Bacon number for an artist. The Oracle of Bacon, which was a project that inspired this project, had a way to measure how much of a center a certain actor was. So we wanted to replicate this, but for artists, and we did this using betweenness centrality. So to calculate the Bacon number, we counted the number of artists each degree away from the artist you inputted. So for Ariana Grande, for example, the number of artists 0 degrees away from her is 1, which is herself. And then using these numbers, we weighted the number of linkable artists by multiplying the degree of the artist times the number of people at that degree. For example, in the image below, you can see Ariana Grande at 1 degree has 38 people. So the weight would be 38 times 1, and it would go like that for the rest of the table. And then to get the final Bacon number, we divide the weighted number of artists by the total number of artists the inputted artist has. And for this, you can see that Ariana Grande's average number is 4.9. Another thing we wanted to find was the most popular or most important artists, and we did this using PageRank. The way it works is it counts the number and quality of links or collaborations an artist has to determine a rough estimate of how important or popular that artist is. We make the assumption that more popular artists are likely to receive links from other popular artists. For example, if someone receives a link from Taylor Swift, we assume they are popular because we know Taylor Swift is popular. We use Markov chains and transition probability and calculate the transition probabilities by getting each artist's score at a certain iteration or the current iteration and divide it by the number of collaborations that artist has. And then after running this algorithm multiple times, we get a stationary distribution of this Markov chain, and where the highest number is the most popular artist and the lowest number is the least popular artist.
So to ensure that our project was working as we developed, we created a bunch of test cases to test the functionality of each of our algorithms. The first test case tested our BFS. And for the first assertion in that case, we inputted the artists The Weeknd and Ariana Grande into the BFS algorithm and generated the shortest path between those 2 artists. We then computed the correct shortest path by hand and compared those two paths to make sure they matched. We also checked that if an artist which wasn't connected to the input artist was inputted into the BFS, it would output that the path was not possible, and we verified that that did work. For our second test case, we ran Prim's algorithm over our graph and generated an MST in the form of a map containing all the vertices and edges that the MST spanned. And after that, we created we solved for the correct MST by hand, and we compared those. For the PageRank algorithm, we created a test case which ran PageRank over our graph and first checked the popularity of certain artists and then checked to find the most popular artist. We then ran the calculations by hand to confirm which artists would be the most popular and what the popularity of the input artists were, and we confirmed that those matched. For between the centrality, we ran our algorithm over the graph to confirm or generate the Bacon tables for the artists The Weeknd, Ariana Grande, and Dina Menzel. And then we compared those to the correct calculated Bacon tables, making sure that all the Bacon number values were the same. And then finally, we had a test case for the connected components, which ran over the graph and counted the number of connected components. And the test case checked that against the actual number of components to make sure they were the same. So there were a couple of main obstacles we faced throughout the development process. The first was that since our graph was unweighted and undirected, there were a bunch of algorithms we wanted to use that we couldn't use. For example, we wanted to use Dijkstra's algorithm originally, but since the graph was unweighted, we found that that algorithm pretty much simplified to a BFS. So we had to get more creative. The reason this was an issue is because we couldn't really think of a weight that would make sense for our graph. Since the artists were the vertices and the songs were the edges, none of the potential metrics that were given by the dataset, such as energy, danceability, or valence, would have really worked. I do think that by finding a metric that works, we could have gotten more robust results and found some interesting connections between our data. But unfortunately for this project, that wasn't possible given the time. The second obstacle we faced was that the CSV was extremely large. We mentioned earlier that the dataset contained over 1.2 data points, which means that all of the algorithms and tests that we ran took forever to run. To circumvent this, we had to create a separate CSV, which contained a fraction of the data points. And by running that, we were able to make our algorithms run much faster. Another issue with having so many data points is that for our visualization, we couldn't see the entire component. Instead, we saw a bunch of unconnected components since we couldn't input all the data. Going hand in hand with that issue, the data that we did get was very messy, since the data set that we downloaded contained columns containing vectors of strings, and for each of these strings, the character distribution was very asymmetrical, meaning some strings contained commas and apostrophes, while some had quotation marks and brackets. So we had to go through those and clean all the data in order to compare them properly. So after we cleaned our data, we found that we actually didn't have enough data points. So what we had to do is we had to change the graph from containing only artists or only songs containing 2 artists to songs containing any number of artists. And that gave us a lot more data points and allowed us to fill in the graph a lot better.
So after we continue to explore our data set and what we could explore with finding out how many connected components there are and different connections in this graph, we found that out of the 80,000 artists we inputted, around 65,000 of those artists were contained in a single connected component, which means a large amount of our data set was all in one connected component. But that being said, many artists were not connected at all. Approximately 8,000 connected components existed within our data set. It was really cool to see how artists collaborated with each other and how artists are related to each other. And throughout our project, we really loved learning more about our favorite artists and how they connected to each other with what songs and the different playlists created by those paths. It was a fun way to find new songs. The graph on the right was our first iteration of our graph, and it contained only songs that had only two artists. In our next iteration of our graph, as we said earlier, we included songs with two or more artists. This graph also only has 20,000 data points, when in our true data file, there's over 80,000 data points.
And that concludes our presentation. Thank you so much for listening to us.